Every day around 1000 terabytes of video is uploaded to YouTube, and to store that much of data you need hundreds of thousands of computers with millions of hard drives inside them. And when you have a system with that many drives, based on the probability calculation that you see here, you can say with near absolute certainty that by the time you finish watching this, one of those drives has died, and yet not a single second of uploaded video is lost. So that raises a question: how does YouTube, or rather Google, the company running it, prevent this from happening? And the answer to that is obvious: money. As a multi-trillion-dollar company, Google, you can just buy that kind of really good computers, that never breaks, right? Wrong. No such computer exists. Statistics and physics still apply to you, even if you're Google. Any computer you run will eventually fail. And when you have hundreds of thousands of them, components failures are norm rather than the exception. That's how it opens. A paper Google published in 2003 called the Google File System. What YouTube runs on today is the successors of the same design. And there is an open source version of this design called HDFS, which basically anyone can download and run, and that became the storage layer that most of big data industry ran on for a decade. This video is an introduction to Google File System and the problem that each of its design decisions solves. By the end of this, you will understand how thousands of computers that are constantly failing add up to a system that hands you back the exact file you asked for. So let's jump in. We first have to understand how your operating system stores your files. You see, your operating systems come with a file system, which is responsible for organizing your files on your computer storage. This file system divides your computer storage into equal-sized blocks. Depending on what file system your operating system uses, the size of these blocks can be different, but it's usually 4 kilobytes. And depending on how much storage you have, the number of these blocks can be higher. For example, if you have 1 terabyte of storage, you can have 268 million blocks. Each one of these blocks has an identifier associated with it. Starting from the first block at 0 all the way to your last block, which on your 1 terabyte storage would be block 268 million. These blocks are where your files are actually stored. Now let's say you have a picture of a cat on your computer with the name cat.png. The total size of this file is 12 kilobytes. To store these 12 kilobytes into these blocks, your operating system will chop this file into 3 parts, each 4 kilobytes. Let's call these parts chunks. Each one of these chunks will be stored in one block, whichever random blocks happen to be available. To be able to later assemble your file from its chunks, your file system stores the address of each one of these blocks in an index table, which is called the master index. This means every file in your file system is a record in the master index, with the information about all of the chunks that make up that file and the block number where each chunk is stored. So when you click on cat.png, the record of those chunks is retrieved from the master index, assembled, and sent back to your operating system to show it to you. But what if the file you're trying to store is bigger than your entire storage capacity? Every day, around 720,000 hours of video are uploaded to YouTube. That's estimated to be around 1,000 terabytes of video data. And that just one day. Tomorrow another 1,000 terabyte comes in, and another one the day after that. The largest enterprise grade storage drive you can get right now, let's say, holds around roughly 250 terabytes, and it costs around 100 grand. So one solution would be to buy a lot of these storage drives and jam them into a supermassive computer that holds all of the YouTube. But you can quickly see why that's not a good idea. Because what if this computer loses power? Or what if the building it's in catches fire? Relying on a single computer like this will lead us to lose all of our data in an instant. Also, this solution is not scalable. There is a limit to how much storage you can add to a single computer and how much requests it can handle. To deal with the risk of a single computer failing and with the scalability, we can take inspiration from how the file system breaks a file down and stores it into multiple blocks on your computer. But instead of multiple blocks, we have multiple separate computers. Each computer with its own storage drive in different geographical locations with independent power sources and have them communicate over a network. When a file comes in, it again chopped into chunks, and each chunk is stored on one of these computers, just like it was stored in a block on your file system. Let's call this the storage computer chunk servers because they store and later serve the chunks. Each one of these chunk servers doesn't just hold one chunk, it can hold many chunks from many different files, like videos. Then we have one master computer, just like the master index on your file system, where it keeps track of each file, its chunks, and the IP address of the chunk server where each chunk is stored. So when a client, which is you, the viewer, comes in and asking for a cat video file, the master will respond with the list of the chunks that make up that video, along with the IP address of the chunk servers where each chunk is stored. The client can then download every chunk and assemble the video. But now, what if one of these chunk servers dies? That means we lose access to an entire chunk of our cat video, and we can't assemble the video again. You might think these temporary outages are rare. It's fine to fail once in a long while because the server will come back and we will get that chunk again, and your assumption about a single server is correct. The probability of any single server failing is very low. In the real world, a single server might fail only about once a year. But when you're dealing with many of these servers, maybe hundreds of thousands or even millions of them, as the number of servers grows, the probability of one or more of these servers failing at any given moment grows too. A year is about 31 million seconds. So across a million servers, that means we have a server failing every 30 seconds or so. And because our system requires every single one of these servers to be online at all times, the failures of even one server interrupts the entire system, which in our case means a server is dying every 30 seconds. And when one server goes down, we lose all of the video chunks that it holds with it. This was the exact type of problem Google was dealing with in 2003. They were building their massive search engine, which had to crawl, index, and store a huge amount of web data. This problem and some other that we will discuss led Google to create GFS, the Google File System. Just like the system that we designed, at its core, the Google File System connects thousands of computers together to store and manage a massive amount of data. Google File System make multiple copies of each one of these chunks and store each copy on a different chunk server. That way, if you lose one of these copies, we still have other copies of that chunk on other servers. Each one of the copies they make of a chunk is called a replica. They call the number of the replicas the replication factor, which is basically how many replicas to make. This number is configured to 3 by default, and we will see why. Now, for each copy, the master server keeps track of the required replication factor and the IP address of all of the chunk servers that hold a replica of that chunk. That way, when one of those chunk servers dies and fails to respond, the client just makes a request to another chunk server that holds a replica of that chunk. But if you think about it, we really didn't solve the root problem here. Having extra copy as protection will buy us time. But you see, if you let this system to run for long enough, eventually all 3 replicas of a chunk will go down, and we'll run into the same state of losing a chunk entirely. GFS solution to this is the heartbeat check. Let me explain. Chunk servers in the system are programmed to send a heartbeat message to the master, let's say every 30 seconds. That's their way of signaling the master that they are alive in the network. And this is how master keeps track of which chunk server holds which chunk. If it doesn't receive a heartbeat for a while, let's say after 3 misses in a row, so about a minute and a half, it will assume that chunk server has died. So it will remove that chunk server from the list of replicas for every chunk it holds. Removing one replica from a chunk lowers the number of actual replicas. If the number of actual replicas drop below the required replication factor for that chunk, the master will try to replicate that chunk to meet the required replication factor again. So it will pick another chunk server that isn't currently holding that chunk and will ask it to copy the chunk from a chunk server that already has a good replica. That way, the number of actual replicas meet the replication factor again. Now we have a system that's constantly healing itself by making sure that at any given moment there are enough replicas available in the system. But what if master dies? The master is the one managing our system and it holds the state of our system in its memory. So just like with the chunks, having just one master puts us at the risk of losing the entire system's availability. To solve that, the master constantly copies every change it makes to a backup master server. This backup master server just keeps receiving those changes and does nothing until it's told to step in. We call this backup master server the failover server because it's what the main master server will fail over to when it fails. Both the main master server and the failover master server report their health status to a health check server. They do that with a heartbeat message at some frequency, just like we saw with the chunk server heartbeat check. When a client wants to reach out to the current master server of the system, it will use a DNS address, let's say master.com, that points to the current master server. If the health check server starts receiving heartbeats from the current master, it will change the DNS name to point to the failover master server. That way, client requests will resolve to the failover master server, which already have almost up-to-date copy of the states, so it can take over the role moving forward. And this cycle continues. So up until now, we only look at Google File System from the perspective of downloading data from it. But it actually gets really interesting when you want to upload a file to this system, because now multiple clients can modify the same chunk at the same time. Let me explain with an example. Let's say you're sharing a spreadsheet with your neighbors that you use to reserve parking spots in your apartment parking. In this spreadsheet, every row is one available slot, and reserving a spot just means adding your name to a row. So now imagine this spreadsheet is stored as one chunk which is replicated across 3 different chunk servers. When you want to add your name to this spreadsheet, or rather the only chunk here, you will request all of the chunk server addresses from the master, and the master will give you all of those addresses. And the simplest way to update this is to send your record straight to all of those chunk servers. And after they confirm the updates, you end up with the exact identical chunks in all of the replicas, and you can park your car in the spot you reserved. Simple enough, right? Now imagine you and your neighbor are trying to reserve the same spot at the exact same time. Both of you will receive the addresses from the master and start sending the updates to the chunk servers. The first chunk server receives your update first, and then your neighbors. So it adds your name first and your neighbor's name below it. But the second chunk server receives your neighbor's update first and then yours. So it adds your neighbor name first and your name below it. And now the chunk and its replicas are out of sync. One copy has your name above your neighbor's, the other has it the other way around. And there is no way to tell which order is the correct one. Essentially, we're in the state the paper call it inconsistent, meaning the data that's supposed to be the same on different server is not the same. So how does GFS fix this? You see, the problem here is that each one of these chunk server sees the order of their updates from its own perspective and not from the perspective of other servers. So if they receive the update from you first and then from your neighbor, that's the order they apply, regardless of whatever order the other server received them in. To fix this, we need to pick a leader from the servers who is responsible for deciding the order. In the paper, this leader server is referred to as the primary. The master is the one who chooses this primary. It also makes sure there is one primary for every chunk at any point of time and keep track of which server that is. Now, when you and your neighbor request a list of chunk servers, the master will provide the list and tell you which one of those chunk servers is the primary. You and your neighbor will receive the list and just like before, send the updates to all of those chunk servers and wait for their reply. After you receive the confirmation from all of those chunk servers that they received the updates, you will ask the primary to announce the update order from its own perspective to all of the other replicas. All of the replicas will receive the update order from the primary, apply that order to the updates that they received before, and then save the chunk, which is the update order from the primary's perspective. And because of that, we end up with identical chunks on all of the servers, no matter how many clients are requesting updates at the same time. Because of these design decisions, GFS is extremely optimized for bandwidth, but not for latency, meaning it can serve a huge amount of data to a lot of clients, but not necessarily be very fast in doing that. And that's a common characteristic of any distributed system design. You identify the requirement of your system and you optimize for those and put the others off the table. Now, I want to ask you a question to test your understanding. Imagine in our Google file system, one of those files becomes extremely popular. For example, it's a viral social media post or something. And a lot of clients requesting that file, or in other words, the chunks associated with it. That means the server holding those chunks need to handle a lot of requests, a lot more than the other servers. The paper refers to this as having hotspots in your system. So my question for you is, how do you go about distributing this load and reducing these hotspots? I highly recommend you read the paper on your own. Maybe you can find the answer of this question by reading the chunk size section of the paper. But for now, let's wrap things up. If you learned something new out of this, consider subscribing and make videos breaking down distributed system like this one.